So, hello, and thank you for signing up for my presentation today. My name is Al Carver-Cubic, and I am a research scientist with the Image Permanence Institute. I'd first like to thank Rare Book School for giving me this opportunity to talk about our research and understanding the mechanical or physical behavior of library and archive materials with changes in relative humidity, or RH. I am affiliated with Rare Book School as faculty. So I teach a course in photograph identification. If, um, if this topic interests you, I encourage you to apply. And if you take a look at the Rare Book School website, you'll see that all of the courses look very interesting and amazing. So if you have not attended Rare Book School, I encourage you to think about it. It's a really cool place. Okay, so as I said, I'm from Image Permanence Institute. I'd like to tell you a little bit about our research center. Uh, Image Permanence Institute, or IPI for short, is an academic research center at the Rochester Institute of Technology. We're dedicated to supporting preservation of cultural heritage collections in libraries, archives, and museums around the world. We do this through several different initiatives. The first is material-based research with a focus on printed media and research on collection storage and transit environments. This research informs our educational tools, our products, and our services, such as our consulting practice. We offer a range of preservation consulting services, from environmental monitoring and data analysis to mechanical system design, consultation, analysis, and optimization. Our experience, as we say, in the field, looking at collections and storage facilities, in turn informs our research. So all of our initiatives are sort of tied together, if you will. So as is often the case, research outcomes often lead to more research questions. So it's important to frame this project within larger scope of IPI research. Therefore, I will first discuss why we are interested in how materials respond to changes in environment. Then I will talk about research we did on moisture and thermal equilibration of library and archive materials. This research then led us to investigate the physical response of library and archive materials. All the research I am presenting on today was funded by the National Endowment for the Humanities. All of IPI's initiatives have an eye on environmental sustainability. For a long time, many collecting institutions took a static approach to environmental management. Typically, this means keeping conditions at a steady temperature and relative humidity. That's usually 70 degrees Fahrenheit and 50% relative humidity, which is really intended for human comfort. So as you can see in this graph, I'll be showing you several graphs, so I'll walk you through each graph that I show you today. So on the left here, we have temperature in Fahrenheit, and on the right, we have relative humidity, 0 to 100%. And you can see that the dark red line is 70 degrees Fahrenheit. The dark red is our temperature, and the light red is the percent relative humidity. And so this is a static temperature and relative humidity. So yeah, so that's just kind of what I wanted to point out here. And this approach can be problematic for several reasons. A form of chemical deterioration called hydrolysis is a primary form of deterioration of organic materials such as paper. So as a general rule, the rate of chemical reactions doubles with every 10 degrees Celsius increase in temperature, thus speeding up hydrolysis. So 70 degrees Fahrenheit is a little too warm for collections. That is, the rate of hydrolysis is a little too fast. Other collections maintain constant conditions at cooler temperatures, 60 degrees Fahrenheit and maybe 40% RH. There's nothing wrong with maintaining these conditions. This will provide a good preservation environment for most library and archive collection materials. And oftentimes, as is in the case with this particular graph, our collections materials and our people are in the same spaces. And so we have to keep the space at temperatures and relative humidity that's appropriate for human comfort. However, maintaining this sort of static environment also uses an incredible amount of energy. So in non-temperate climates, like Rochester, where I live, the HVAC systems are constantly fighting the outdoor highs and lows in both temperature and relative humidity, and HVAC systems aren't typically designed for this. So you could probably see my thing there, so I'll hide that. Sorry about that. That energy usage translates not only to a huge carbon footprint, but also to money. Maintaining constant conditions is expensive. So in terms of achieving the goal of all collecting institutions, providing the best preservation environment we can to help these materials last as long as possible, a static approach at cool temperatures and moderate relative humidity is absolutely fine. However, cultural institutions are facing financial constraints due to a lot of factors. With the current economic situation, institutions are especially struggling. HVAC operation is a big bill for most institutions. So returning to this idea of environmental sustainability, much of our research focuses on creating preservation guidelines that take what's called a dynamic approach to storage environmental management. A dynamic approach means set points are adjusted seasonally in order to keep spaces cooler and drier in the winter and slightly warmer and more humid in the summer, while staying with the temperature within the temperature and relative humidity parameters that are considered acceptable for maintaining a preservation environment. The temperature parameters are largely collection material dependent, but generally we like to keep things below 70 degrees Fahrenheit. Relative humidity should be kept between 30 and 60% relative humidity, again, depending on your collection materials. Also, depending on your geographic location and your building envelope, you may also try nightly and weekend settings adjustments. So that means either lowering or raising the temperature for nights and weekends, so you're not fighting against what's happening outside quite as much. And some institutions change set points, and some actually shut down the HVAC system during nights and weekends entirely when the building isn't occupied. We find that this is particularly effective in institutions in which the collection space is shared with staff or visitors. So if you're interested in better understanding and even implementing some of these methods, like temperature and RH adjustments and nightly and weekend shutdowns, IPI has a lot of resources that can help you, and I'll talk about those at the end of my presentation. So this leads to the question, how do we know that a dynamic environmental approach works and is safe for your collection? That is, how do we know that letting your temperature and relative humidity adjust for seasons or do nightly and weekend settings adjustments and shutdowns is okay for your collection? And the answer is short, it's science-based research. For several years, we have been conducting research on temperature and moisture equilibration of library and archive collections and storage. That is, when do collections and storage actually feel changes in the ambient environment? Much of this research is led by my colleague Jean-Louis Bigardon, and to briefly summarize his research, data loggers were placed inside the cavity at the center of books, as well as stacks of paper-based objects in various storage configurations and different enclosure types. And just as a note, you can see that we have cut a hole in the center of this book and placed a temperature and relative humidity data logger in the middle of it. I'd just like to say that in all of our research, the books and collections and other collections type materials that we use are not actually part of any collection. They all have unknown histories and were collected by IPI for the purpose of research. For example, a lot of the books that we have were being deaccessioned by libraries. So to talk about that research a little bit, what we found is that thermal equilibration, that is changes in temperature, are felt very rapidly. It takes about 4 hours for 1,000 photographs in a metal edge cardboard box to thermally equilibrate, that is to feel that change in temperature. So I'll walk you through what's going on in this slide first. So here we have several different kinds of storage boxes. In the center are metal edged cardboard boxes. Those of you who work with collections, these boxes may look very familiar to you. These are pretty typical for storing paper-based collection objects. And so what we did is we put the logger inside the box, and in the middle of the stack of photographs that were in this box. And we changed the temperature in our walk-in temperature and humidity controlled vault. And it took about 1,000 prints within this cardboard box about 4 hours to feel a change in temperature. And that's what's represented here in this graph. On the left, from 0 degrees Celsius to 40 degrees Celsius. The dark red line is the ambient temperature. So that's the temperature as it goes up and down in this temperature and humidity controlled walk-in chamber. And the blue line is the center of this cardboard box, sort of the center of those objects in that cardboard box. And you can see that it follows the ambient very closely, and there's just a little bit of a lag as it reaches its top temperature or its lower temperature here. And this is that sort of 4-hour period in which it takes to equilibrate. Each one of these cells is a 24-hour period. So we did a 24-hour cycle up, down with the temperature. And then this chart is just sort of summarizing some of what we found. Okay. So then when it comes to moisture equilibration, we found that it takes about a month or more for an entire book or a stack of paper-based objects like photographs in a box to equilibrate to a change in the ambient relative humidity. So in this case, we're looking at the book. So here's that picture again, where we put a temperature and humidity data logger in the center of a book. And this graph is showing both temperature and relative humidity. So again, the top will look pretty familiar. The dark blue is the ambient temperature, the temperature inside the vault. And then the red is the temperature inside the core of the book. The light blue here at the bottom, this is where I want you to focus. The light blue is the ambient relative humidity going up, down, and the light red is the relative humidity in the center of the book. And you can see in the 24-hour cycle, the book never fully equilibrates. It never fully comes to the same relative humidity as what's happening outside of it. In order for this red line to actually reach the relative humidity here, which is at 50%, I believe, it would take a month. So you'd have to be in this environment for a month for it to fully feel a change in relative humidity. And again, this chart just sort of briefly summarizes that, some of the findings for that. So Jean-Louis also tested how enclosures affect equilibration. He tested a metal edge cardboard box, a museum case or cylinder case, and a portfolio box. So this graph compares the moisture equilibration between the cardboard box and the museum case or cylinder case. Moisture equilibration is slower in the museum case, or in other words, the case is better at buffering against changes in relative humidity. So again, here we have 0 to 100% relative humidity is our scale in blue, and this is over time. And a 24-hour period is each cell here. And the green in this case is our ambient relative humidity going up, down, up, down. The blue is the cardboard box, and the red is the museum case. And you can see that the museum case, the up downs are a little less, right? It just isn't going up as high and down as low with the relative ambient relative humidity in the chamber. So the conclusions from this research say that daily fluctuations in relative humidity are not fully felt by collection objects and therefore do not drastically impact the preservation of objects. Changes in temperature are allowable, while chemical deterioration is very slow. So if we have a short-term high in temperature, the chemical reaction is so slow that it's not really long enough for it to fully feel that sort of thermal change and sort of push forward that chemical reaction. A long-term high in temperature will have far more impact on the long-term preservation than these sort of brief excursions. So, however, while full equilibration and relative humidity is very slow, we know that moisture diffuses from the outside in, so that the outside of a surface of a book, for example, will experience a change in relative humidity first. And so that led us to our next set of questions. However, books are really difficult to study. They are complex, composite, three-dimensional objects, and they're made from a wide range of materials. Books are typically made from paper, parchment, leather, cloth, board made of paper, straw, or wood, and as well as lots of other organic materials. And these materials are all hygroscopic, meaning that they absorb moisture from the air. With a change in relative humidity, their hygroscopic response is physical. They expand and contract as they absorb and desorb moisture. So if the relative humidity increases, the object will absorb moisture, it will expand, and vice versa. However, each material in a bound volume may expand and contract to different degrees, potentially leading to physical deformation. So this video that I'm going to show you was made by my colleague, Andrew Lurwell. And what we see here is the response of various different books to changes in relative humidity between 60% and 25% RH and then back to 60%. I'll play it again. So what you see here is that as the RH increases, the books contract, causing the covers to lift. This area below is highlighting the part of the books that are responding. So the temperature change, the RH changes, the books respond. There you go. Of particular concern are vellum-bound books, as they are particularly responsive to RH. We have heard stories of a sudden drop in RH due to an HVAC failure, resulting in books flying off the shelves, like the scene in Ghostbusters. This led us to ask another set of questions. How fast and to what extent does the skin of a book or the binding feel a change in relative humidity? Under what environmental conditions will permanent physical deformation occur? To try and answer these questions, we used a photogrammetry technique called digital image correlation, or DIC for short. Photogrammetry is the use of photography to make measurements, particularly measurements in distance. This tool allows us to measure physical behavior of two-dimensional library and archive materials, including unrestrained single sheets of paper, parchment, cloth, and leather, as well as three-dimensional structures like bound volumes. So this is sort of an image of our setup for looking at books. Okay, so how does DIC work? DIC requires the test samples to have high contrast, random pattern of speckled dots on the sample surface, either naturally occurring or applied. We partnered with our friends at the Cary Special Collection Library at RIT, and we used letterpress and printer's ink to print a dot pattern on single sheets of material, which is seen here. Went through the letterpress. Again, we tested various papers, parchment, book, cloth, and leather, all of which we put through the letterpress. For the books, we couldn't put those through a press, so we applied the same pattern using screen printing, and we partnered with our colleagues in RIT in the School of Printing. We tested books with full vellum bindings, full paper bindings, full half and quarter leather bindings, full half and quarter cloth bindings. And again, just to throw this out there, all the book samples were collected and all the paper and parchment samples were collected by IPI with unknown histories and are fairly representative of collections. Test samples and the DIC equipment were placed in our temperature and relative humidity controlled walk-in chamber. So these are views inside that temperature and humidity controlled chamber. These images show the testing here for the 2D single sheet materials and here for our three-dimensional objects, our books. Two cameras were mounted on a crossbar, which was mounted to a tripod. So this image I think shows it better. Here's our tripod. There's a bar coming out here, which you can see here, and then a crossbar. And here we have our arrows pointing to the two cameras. The two cameras imaged all of the samples in stereo, and we imaged at regular intervals. The cameras were set to image every 5 minutes during each of our testing profile. And these images are parchment samples. So here's the setup here, and you can see the two cameras, and these are the images, or examples of the images that those two cameras took, left and right in stereo. We used 6 different testing profiles, and these testing profiles were used for each material type and all the bound volumes. Each profile began at 50% relative humidity and 20 degrees Celsius, which is 68 degrees Fahrenheit. So here at the top, we have 3 what we call desorption profiles. That is, the relative humidity decreased. Each starts at 50% relative humidity. One decreases to 30% and then increases back to 50%. The next one to 20%, and the next one to 10%. We have two absorption profiles. The first goes to 60% and then back down to 50. And the next one goes to 70% relative humidity, back down to 50. And then finally, we have one that sort of oscillated up and down between 50% to 70% rather, back to 50, down to 30, and up and down and up and down. What we're seeing here is we have this sort of initial period at 50%, and then each one of these, it took 2 hours for the relative humidity to change. That's called a ramp. And then it stayed at that constant relative humidity for 12 hours. This is what's called a soak. Then it ramped back up and then had a longer soak period at the end. We chose a 12-hour soak period and this sort of 2-hour ramp because it represents an extreme change. That is what we believe to be the worst case scenario. All of the images were uploaded to specially designed software, which tracks the movement of applied speckles in 3 dimensions. Algorithms calculate in-plane and out-of-plane displacement, as well as the strain for the material tested. Data is produced as numerical data that can be graphed, as well as 2D and 3D maps that can be animated. So here are the animated 2D and 3D maps. So shown here are parchment samples tested with profile 6, which you can see up here in the corner, the one that went up and down, increasing and decreasing in relative humidity. The video on the left is 2 dimensions, and on the right is the same sample in 3D. As the relative humidity changes, the object physically responds by expanding and contracting. The scale on the right of each video is color-coded, showing the strain level experienced by the object, the extent of its change. Here is what DIC data from that same sample looks like when we graph it. Positive strain numbers, so these numbers going up, so it always starts at 0% strain, right? And then we add relative humidity, we increase relative humidity, the strain goes up. That shows expansion, and then it decreases, and then these negative numbers show contraction. So I think now is probably a good time for some definitions, a little more background in this general area of research. In order to determine the point at which a material will permanently deform, we look to mechanical engineering testing techniques that measure strain. DIC is a relatively new technique. The Smithsonian Museum Conservation Institute did a significant amount of work on material strength under the leadership of Marion Mecklenburg, beginning, I think, in the 1980s. Their focus was on materials used for paintings, although they did explore some other organic materials. They used tensile testing to determine the strength of materials in which they applied a load or force to the material, measuring stress and strain. They also looked at dimensional responsive materials to changes in RH. So usually tensile testing is done in an apparatus called an extensometer, and this is sort of a diagram or a drawing of a typical extensometer in which you have these 2 clamps and your material is placed between the clamps. This top one is fixed and you add a load or a force here. So what this does is it measures stress and strain. So stress is the resistance or counterforce of the material under the external load or force. So here's your external load or force, and you have these gauges and things on here, which will then measure sort of the counterforce of this external load or force by the material. Stress can be tensile, compressive, or shear. Strain rather, is the ratio of the stress-induced change in length of a material to its original length. It's expressed as a percentage. So in other words, it measures the extent of change in length of a material due to stress-induced extension or compression. How much did it change? Most materials have what is called an elastic region, a plastic region, and a yield point. Hang in there with me. The elastic region is where most objects expand or contract under an applied force and return to their original shape when the applied force is removed. This is reversible change. So think of this toy from my childhood anyway, I think it still exists, called Stretch Armstrong, or even a rubber band. You pull it, you pull it, you pull it, you let go, and it bounces back to its original shape. It's elastic, okay? That's the elastic region. The plastic region is where objects do not return to their original shape. This is irreversible change. So if you were to pull and pull and pull Stretch Armstrong and let go, and his arms would still be all, wonky and wobbly and not come back, then we would have reached his plastic region. He did not return. It also measures something called the yield point. The yield point is the stress at which a material begins to deform plastically. Prior to the yield point, the material will deform elastically and will return to its original shape when the applied stress is removed. So again, if we keep stretching, Stretch Armstrong, there's going to be a point where we hit what's called the yield point. If we keep going, he won't return. But if we stop, he will return back to his original shape. So this stress-strain data is expressed as a stress-strain curve, which shows the relationship between stress and strain of the materials tested. So let me explain this graph. So we have our stress. So this is our applied load. That extensometer, it's pulling. We're applying a force. We're pulling down on the object, and as we pull on the object, it elongates. Right? We get strain. It gets longer, longer, longer. Right? This is our yield point. If we let go at this point, it'll bounce back to its original shape. If we keep pulling on it, if we keep applying a force, it will hit the plastic region and it won't return. And if we keep applying the force, it will eventually break. I believe this is what happened to Stretch's head, is he hit the breaking point or rupture point. The Smithsonian Museum Conservation Institute lab determined that the yield point of most organic materials is 0.4% strain. That is only when the materials are restrained, like a canvas in a stretcher or perhaps a bound book. That relative humidity related dimensional change can cause enough strain for damage to occur. So it's only if you hit 4% strain, only if it's restrained will any damage occur. If it's not restrained, it should be fine. So what does DIC tell us? And what does it not tell us? I'll begin with what it can't do. DIC alone, in the application in which we are using it, we cannot measure stress. It only gives strain data. That is, it only gives the extent at which something elongates, expands, or contracts. The load is a change in moisture content. That is how much moisture is in the material. And this can't be converted into stress data. It's just not the same. So to gather stress data, we would have to perform a tensile test using an extensometer, which of course we can't do with three-dimensional objects like a book. Therefore, we cannot generate this here stress-strain curve, which means we cannot determine the elastic point, the yield point, and the plastic region. That is, we cannot determine at what point we'll find permanent deformation through data alone. And just to point out this graph, this is another, this is more data from the DIC project, in which we had a single increase in relative humidity and then a long soak period or static period of relative humidity. And so you can see that the relative humidity increased, the object expanded, and this is our strain data. In this application, however, it does allow us to track moisture diffusion, and it does give accurate data as to the extent of expansion and contraction of the object. This allows us to determine when the skin of the book or a single sheet of material feels a change in RH and to what extent. This information is extremely informative and is a really good complement to the moisture equilibration data for collection object storage that I discussed earlier. Shown here on the left is the percent moisture equilibration data taken from the core of a book. As the ambient RH increases, the internal RH of the book begins to rise as the book absorbed moisture until it reached equilibration. The right is that same graph. It's the mean primary strain of a piece of paper. As the ambient RH increased, the paper absorbed moisture and expanded until it reached equilibration. You can see that these graphs do indeed look pretty similar to one another as well. So the shape of these graphs are, again, similar to one another, and they also follow what's expected based on the laws of moisture diffusion. And these are called Fick's law, named after a guy named Fick. In a nutshell, as it's applied to our topic, Fick's law says, if there is higher concentration of water vapor in the air and a lower concentration in the material, like a piece of paper or a book, water will diffuse from the air into your object till there are equal amounts of water vapor in the room and in the object. And this is equilibrium. Okay, so we start off with more moisture vapor in the air than in the object. The object equilibrated, so now there's equal amounts of vapor, of water vapor in the object and in the air. And this also happens in reverse. So if there's less water vapor in the air than there is in the object, water will come out of the object and into the air. This occurs very quickly at first and then slows down as the material reaches equilibrium. And again, the material will physically respond by expanding as it gains water. Another hallmark of moisture diffusion is a phenomenon called hysteresis. Adsorption hysteresis is a phenomenon in which the moisture content of hygroscopic material differs depending on if the material is diffusing into or out of the material. Typically, the material has more water at a given RH during desorption than during absorption. When the DIC data is plotted as percent strain versus RH, it has the typical appearance of a hysteresis loop. So again, I'll explain these graphs. The graph on the left is paper sample number 32. The scale on the left is our percent relative humidity, and on the right is strain. The blue line is the ambient relative humidity in the chamber. So again, we started at 50%, the RH increased to 70%, and then decreased to 50%. The strain, which is the yellow line, followed the RH, right? It goes up, and then it comes back down. If we take the same data, the yellow line, and we graph it as percent strain over relative humidity, what we get is this loop. And so this shows the RH increasing, so our strain increases, and this is that soak period here, right? This sort of squiggle line. And then the RH decreases, and our object begins to contract. And you can see, for example, here at 65 relative humidity, we have more water on the way down than we did on the way up. And this behavior is typical of nearly all organic hygroscopic materials and gives further evidence that the DIC data is an indirect measurement of moisture diffusion. Okay, so if this weren't convincing enough, if we consider strain data as an indirect measurement of moisture diffusion and we apply Fick's law, the results are exactly as expected. So in this graph, my colleague Doug Nishimura used Fick's law to calculate what we would expect the rate of moisture diffusion to be for this particular material. Again, paper sample number 32, the same one. So the red line is represented in what we would expect out of this material in terms of its behavior with moisture diffusion. And the blue line is our actual data. So they fit the model pretty well, I would say. So now that we've figured out what we can and cannot learn from this tool, the next step is to determine what our data actually means. I'd also like to just throw in there, we had a double rainbow in Rochester on Friday and it was glorious. Okay, so let's first look at the desorption profile where we started at 50% RH and the decrease to 30%, 20%, and 10% RH. So shown here is DIC data that's represented as graphs. On the left-hand side of each graph is the percent RH, which is represented by the blue line. On the right of each graph is the mean percent strain, represented by the yellow line, that is the percentage of expansion and contraction. As the RH decreases, the material very quickly responds by contracting, and we see that as negative strain. The rate of contraction slows, the material reaches moisture equilibration. Again, according to Fick's law, this is what we expect. It happens fast and then slows down. And this is true for both the single sheets of material, which is shown at the top, and the bound volume, which is shown at the bottom. These are both this is a parchment sample and a vellum bound book. When the RH returns to 50% relative humidity, the materials respond again by absorbing moisture, returning to or near 0% strain. So you can see we come back to where we started. So that is, it's returning to the size it was in the beginning. And the general pattern is similar to all the single sheet materials in all of the books tested. We made some really interesting observations when we looked at the data for all the objects tested. So first, for each 10% decrease in relative humidity, the strain or contraction of the object nearly doubled. Regardless of test samples, everything returned near to or near 0% strain when the RH returned to 50%. Visual observations showed no damage occurred to any of the books or single sheet of material samples, and none of our books flew off the shelves. So what we can see in this graph is the red line is the profile in which we went to 30% RH. The yellow line is when we went to 20% RH, and the green line is when we went to 10% RH. With each 10% decrease in RH, our strain nearly doubles. Again, this example is a vellum-bound book, but this was true for all of the books and all of the single sheets of material. Data from our absorption profiles follow a very similar pattern. As the RH increased, the objects expanded, showing positive strain. The rate slowed as the objects neared equilibrium. As the RH decreased back to 50%, objects contracted. Similar to the absorption test, the strain nearly doubled with each 10% increase in RH. So again, the red here is the profile in which we went to 60%, and this is when we went to 70%. You can see that the strain that we reached is nearly double. So here's just another way to look at the data showing this phenomenon of doubling in strain with each 10% increase or decrease in RH. Okay, I'll walk you, this is a different kind of graph. We haven't seen something like this yet, so I'm gonna walk you through it. Our scale here is percent strain. Each of these color bars represents a different profile. What I did is I took the data point at the end of the soak period at our sort of peak RH or sort of lower end of RH. So the very end of our profile in which we decreased to 30% RH, I grabbed that data point and we graphed it. And so I have a full vellum book, half leather book, full leather book, parchment, paper, leather, and cloth. And you can see here are the desorption profiles. Again, 30%, 20%, and 10%. And the absorption profiles, 60% and 70% RH. In each of these cases, our strain doubles with each either decrease or increase in RH. So here we have a doubling in negative strain, and here we have a doubling in positive strain. So expansion and compression, contraction. These red lines represent the yield point determined by the scientists at the Smithsonian. And so this is the one where they said, if you hit 0.4% strain, you will likely experience permanent deformation. But as I said, when we hit these sort of extremes to 20%, 10% relative humidity, again, the 30% and the 60% are within what we consider the safe zone, like what's acceptable for relative humidity for most collection materials. But we can see, you know, some of these objects, when we really hit these lows or these highs, we go past the red line. But I did say that we didn't see any permanent deformation. And so this is a point where I'd like to explain a concept called proofing. So proofing is a concept in which we say, if a collection material, such as a book, has already experienced an extreme in relative humidity. So let's say our vellum-bound book has already seen 10% relative humidity from the day that it was constructed to today, which it likely has. That means that any damage that's occurred to that book has happened. And if we hit 10% again, you know, if that book feels 10% relative humidity again, it's not going to experience any more damage. It's not going to become more damaged. So once you've hit that high of relative humidity, 70% in this case, right, it's not going to become more damaged by hitting that high yet again. Hopefully that makes sense. And again, please feel free to ask questions if I need to explain something further or be more clear. So I'd like to come back to this graph. Something that you may have noticed that I haven't pointed out yet is that our book does not return to 0% strain. And this is consistent across all the materials we tested in all the bound volumes. So again, I said that we didn't see any damage, which we really didn't. But our data shows us that we didn't come back to 0, right? So does this residual strain here, does this amount to permanent deformation? Right, so we still have 0.05% strain in this object. Does this mean that we permanently deformed our object? And the short answer is no, we haven't. Paper samples were placed in our temperature and relative humidity chamber, and we ran profile 5, which was where we began at 50% relative humidity, we increased to 70%, we returned to 50%. Using the moisture meter, which is this object right here, this apparatus, we measured the moisture content of each paper sample. We measured it at the beginning. We measured it at the end of this static RH, or soak period. And we measured it a third time at the very end of the profile, at the very end of the experiment. And each sample had a higher moisture content at the end of the test. Therefore, the higher strain at the end of the test is indicative of a higher moisture content in the paper. So there's just still water in there. And this is consistent with the results from our storage environment research, in which we have found that moisture desorption is slower than absorption. So again, we just have to let it stay at 50% for a really long time to drive off the rest of that water that we put into it. Another way you can do it is you can actually increase the temperature slightly, and an increase in temperature will push some water out of it, and then that will sort of bring the strain back down or remove some of the water. So our conclusions. We learned some things which we can and cannot do with DIC, but I would say more importantly, we learned that dynamic environmental management is safe for your collection. As long as you stay within the recommended RH limits of 30 to 60% RH, you can implement this dynamic environmental management. And your collection's materials will not likely experience any physical damage kind of within this range. If you exceed 60% RH, and if you go down to 20% RH, especially for a long period of time, you may see some damage, particularly if those objects have never experienced those highs and lows before. Another thing which we discovered, which, when we do any kind of research, we do what we hope to be an exhaustive literature search and literature review. And I have not read this in any literature, so I believe this is a new finding that with every 10% increase or decrease in RH, strain doubles. And I think that's pretty exciting finding out of this research. So to kind of wrap things up, as I said earlier, research often leads to more research questions. So we have continued to look at how changes in environment impact collection objects. Currently underway is research that is looking into the effects of temperature change on moisture content of objects. So again, if we increase or decrease temperature, that actually pushes water in and out of an object. This project is also looking at how temperature change can influence the ambient RH. And in the same project, we're considering what temperature and relative humidity combinations might yield the same moisture content within an object. The idea is that by using these combinations of the sort of sweet spot, right, of constant moisture content, we can apply this to storage and use spaces. And so when we transition an object from a storage space to a use space, such as like a reading room, the object won't experience any change in moisture content. Therefore, it won't experience any physical change either. So you won't see your book sort of moving with change in moisture content. I'd actually like to just return to the conclusions and just add a final thought, is that You know, when we saw that video of the book sort of opening and closing and opening and closing, just because your materials are physically responding doesn't mean that they're being damaged, okay? So you may see an object physically respond to a change in relative humidity, but that doesn't necessarily mean that there's permanent damage. It just means that the moisture content is changing within that material and it's physically responding. So as long as, again, we stay within these recommended limits, you should be fine. Again, I promised that I would share any continue learning opportunities, or if you'd like to learn more about dynamic environmental management, you can visit the Image Permanence Institute website. We have a couple publications. One is just a guide to sustainable preservation practice, and the other one is actually implementing sustainable energy saving strategies. Both of these have free downloads. We also have a free recorded webinar series available on our website. I believe these are both under the education section of the website. And then also on the Connecting to Collections Care, I did a webinar called Storage Environments, the Big Picture, which gives the big picture to storage environments. It's similar to this talk, but it's a little over an hour long, and some additional information about storage environments. Again, I'd like to think we're a book school. I'd also like to thank my colleagues, James Riley, Jean-Louis Bigardon, Douglas Nishimura, Andrew Lurwall, and as always, the National Endowment for Humanities for funding this research. So with that, I will stop sharing, and if anybody has any questions, I am more than happy to answer them. And I believe our friends at Rare Book School will help me with that.
Indeed. Al, thank you so much for that talk. That was fascinating. My name is Laura Idem. I'm the Rare Book School Program Manager, and I'm joined by my colleague, Neil Curtis. We're going to take turns moderating your questions this evening. Our first question comes from Anjali Jain, who asks, how would one know if a collection object has experienced extreme conditions in the past and has already endured all the damage that can happen?
Yeah, that's a really great question. And the answer isn't simple. The answer is often, it depends. Oftentimes, if you know the history of your object and you know kind of where the object, if you will, has lived. So, for example, if you have an object from, let's say, the Navajo Native American tribe here in the United States, and they're located in the Southwest desert, it's really dry there. And so it has likely experienced very low relative humidity. And so if that object gets to be at 10% RH, that's probably better for it, actually. It's going to be fine. However, if you take that object and it's only ever experienced 10, 20, 30% RH, and you put it in a situation of 60% RH, you might actually cause damage to it. So a lot of it is about knowing your collection, knowing the history of the objects in the collection, and what kind of lives they have lived. We have a vellum-bound book that was probably made in Europe. It can get really humid there, and it can get really dry there. And so same as here, it gets really humid and really dry, and I'm looking at the object and I'm thinking, actually, it looks great. Another thing, just as a side note about vellum, we're really worried about vellum. Everybody's really paranoid about vellum and parchment because it's so responsive to relative humidity. Those of you who are bibliophiles and are knowledgeable about book materials have likely found that vellum's like a really sturdy material. It takes a lot actually for it to split like the example that I showed. So also it is material dependent. Vellum and parchment have this incredible absorption ability, but they're pretty sturdy materials. So yeah, I guess that's the answer is you won't know by looking at it. What you will know is just by the history of the object.
Thanks, Al. Our next question comes from Connor. With proofing, is this true even with multimedia materials like a painting on canvas? Because repeated changes in relative humidity, even to identical levels, cause more damage because of how the different materials react to relative humidity?
That's a good question, and the answer is I don't know. I'm not as knowledgeable about paintings and those materials as I'd like to be. But I can point you to the author, I believe, of this idea. I I can't remember exactly who wrote it. It was either Stefan Michalski or Mark McCormick Goodhart. Um, and if Rare Book School has your information, I can find the article actually and send it because it's really interesting. Yeah, and I know, paintings are kind of it's their own special animal for sure. I'm more knowledgeable about sort of basic library and archive materials.
All right, thank you. Our next question is, do you have any plans to study the behavior of parchment in laminated systems such as bookbinding and manuscript paint? How do the different equilibrium responses of these components to changes in RH allow us to predict physical disassociation of the layers?
Yeah, that's a good question too. I don't have any plans right now to study specifically that. Uh, one of the so because IPI is focused on preservation research or preventive conservation, we like to look at big picture ideas. So we're really interested in how the entire collection behaves. We don't often look at really specific materials or material behavior like that unless we have something that's sort of like a big red flag. Like we did do a big study on like cellulose acetate film because it was kind of an emergency as the material is deteriorating rapidly in collections. But our answers to that even are big picture answers, right? Big scope answers. How do you care for your entire collection? So that's not something that I have any plans to study. I would look to conservation science and conservation scientists to study that particular question. Yeah, I hope that answers the question. I mean, kind of.
Great, thanks. Our next question is from Michael Lear. So in your time-lapse video showing book covers open and then close, was contraction or low relative humidity responsible for the covers opening?
Yeah.
And expansion, higher relative humidity responsible for the covers closing?
Yes, that's exactly it. The spine of the book acts like a lever. So as it contracts, right, the covers lift.
All right. Our next question is, have you seen any fungus growth?
Actually, not in my experiments, but my colleague did. In the project that we're working on right now with temperature transitions, it did get very humid for a long period of time because he's basically putting the materials in the walk-in chamber and letting them equilibrate for like three to 4 weeks so they fully equilibrate. And yeah, we got some mold. Yep. Oops.
And a kind of related question from Hannah Callahan. First, she thanks you for your great presentation. She's wondering how this study addressed or considered factors like mold growth and rot, for example, organic deteriorating factors that are encouraged by increases in heat and moisture. Does the same apply? In other words, does this study indicate that that kind of deterioration is not encouraged by this range of fluctuation?
Yeah, within the 30% and sort of 55-60% RH, you're going to be fine as far as mold germination goes. It's not until you exceed sort of 65% RH and get into like 70% that we actually start to see mold germination, and that's just pretty much true. And that's sort of a general rule of thumb. I will say that in our field, sort of in the field, if you will, in our consulting, we do find mold when the data says there shouldn't be mold. And sometimes it's because of the location of collections objects by the in sort of proximity to the air handler. And so you have sort of cold, humid air blasting out, and you might have a shelf of books right there. Right. And so you have all the humidity that's supposed to be humidifying the entire storage facility sort of blasting this shelf. We also find it a lot with movable shelving. And so what happens is we get little pockets of mold in movable shelving because the shelves are too close and the moisture, as we saw in that little video, the water is sort of coming in and out, and constantly equilibrating, right? Really, that video should have just kept showing moisture going in and out, in and out, in and out, because that's what's happening. But if there's nowhere for it to go, it kind of gets trapped in there, and you end up with like a pocket of too much moisture content, basically. One of the topics that my colleague and coworker, Kelly Krish, is wanting to study is actually is mold. And why is it that we have mold when the data says there shouldn't be mold? Obviously, in those two instances that I gave, we know why we have mold, but sometimes we really don't. And so, yeah, it does happen. We really don't know why. And it has to do with the complexities of how water is in objects. It's I won't go into it now, but it gets complex. And so yeah, it's something she's definitely hoping to study, and has come up with some really clever ways to approach it that don't require us growing mold, because it's dangerous. So yeah, but like as a general rule of thumb, if you keep things kind of at 50% or lower, for sure, um, you shouldn't have mold. And the lower range, below 30%, is you actually lose water. Around 20-25%, you lose water that's part of the structure of the material. So all hygroscopic material has water that's part of the object. And if you lose that water permanently, you can't get it back. And that's when the object becomes like permanently brittle. One of the reasons an object can become permanently brittle.
So interesting. Our next question comes from Kelly Rylance, who asks, do you have recommendations for oversizing enclosures to facilitate safe expansion or contraction of their contents?
I'm not sure I fully understand the question, but I think I do. So if you have a two-dimensional object and you're framing it, oftentimes if we're using corners, or sometimes we use like slings of paper, we make sure that they fit loosely, right? You don't want to cram the corner all the way tight down onto the corner of the object. You want to give it a little bit of wiggle room, and that does allow for expansion and contraction. In France, it's really popular to do what's called a French inlay, which they actually, it's don't do this at home, have a trained conservator do it, but they actually use like Japanese tissue paper and make a window inside the mat board, and then use like wheat starch paste and adhere the tissue to both the object and the mat board. That will allow the object to expand and contract. Within housings for three-dimensional objects, you always want to have a little bit of space. You don't want the object to be really tight in there. You don't want it to be rolling around and flopping about, but you want, enough space. But, that space is really like millimeters. It doesn't need to be a large amount of space.
And I see that Kelly has posted a clarifying comment saying, my question has more to do with Hollinger boxes, mannequin boxes, say full of folders of multiple sheets of paper.
Oh, you know what? They're probably fine. We like to put things in boxes that fit. Again, if it fits in there nicely, an 8 by 10 should fit in the 8 by 10 box, and so on and so forth. And you definitely want to modify your boxes so that things aren't flopping around and moving about in there. But really, it does take at least a month for full moisture equilibration. And so the amount of expansion and contraction that will be felt by your object is pretty minimal. And when we were looking at the strain, I could have shown that as actual like dimensions in millimeters. Its expansion and contraction is very minor. So unless it's like way too tight fitting, you should be fine. Yeah, it's really when we have, and also all of that moisture has to move through all of those objects, right? So it definitely affects the top object first and the box itself first, but the middle object, that water has to move through each object on top of it before it makes its way out, So yeah, it'll be fine.
Great. Next question comes from Jim Stokes. He'd like to know, did your research show any changes or impact to the ink on the objects?
No, it didn't. So we use the letterpress ink, and the reason why we use it is because up until the 1960s, all printed material were printed with letterpress. All books are printed with letterpress, and so we know it to be stable. And so that that felt like a good choice. And the screen printing ink was kind of like was a kind of resinous ink. It had like a solvent in it, that it was very stinky. Um, and so it also kind of had some pliability to it. And so we didn't have any problems there. Some of the test materials that we used were historic documents. Again, nothing of any real importance or any known histories. Land titles and things on parchment from like whatever. Um, and yeah, and that ink too it wasn't friable. It didn't come off.
All right, thank you.
Can I just add one thing?
Oh, yes.
If you did have like painted vellum, like Gaussian vellum, um, those are much more sensitive. With that expansion and contraction, the paint will likely pop off. It's not something I've studied directly. It's just sort of one of those things in the back of my head. So if you have vellum with paint on it, you probably do want to keep it in as steady of a relative humidity as you can, or maybe create a microenvironment for it. Okay, sorry.
Oh, no, thank you. Our next comment and question, first of all, thanks very much for an amazing presentation about the mold. From what RH percentage was it perceived?
Oh, in our vault, yeah. You know what? It's a testing chamber, and so we can go as high as like 80% RH. And I think he was running at 80% for a while. Yeah, that's a recipe for mold. I mean, listen, like mold will grow pretty much anywhere at any temperature. So, as my colleague Doug likes to say, he has mold in his refrigerator. Um, we've all found that like leftovers that got pushed to the back and went, oh God, what is that? Um, yeah, it's those, but our refrigerators are also humid. That's why we have the vegetable drawers, because that vegetable drawer actually moderates the relative humidity to a better RH for your vegetables. So really, anything for a long period of time above 65% RH, you have the potential for mold. That doesn't mean you're going to have mold, you have the potential for mold. That's when mold starts to germinate and germinate more rapidly. So yeah. But yeah, if you're 80% per month, you're gonna have mold. When it comes to water emergencies, which we're seeing so many more of, it's not just the objects getting wet that we're concerned about. It's the mold to the materials, but also the building. Because the RH spikes because you have so much water. So.
Great, and we have a follow-up from Maria Alejandra, who had asked about fungus growth before. She clarifies that the question about fungus growth and mold growth was because they have many changes in relative humidity percentage levels, although they use air conditioning, and they have mold growth. So
Yeah. Yeah, and no. Many people have mold. It's a big problem. I would say it's probably the number one problem in collections, pretty much anywhere, except for maybe the desert, right? The dry desert. But yeah, it's really those sustained periods of higher relative humidity where you're in trouble. We have IPI. One of our resources is called eClimate Notebook, and you can if you use a digital data logger, a temperature and humidity data logger, it sort of collects the temperature and relative humidity data, and then you can take that data and you can download it into eClimate Notebook, and it graphs it for you. And so that graph that I showed you from Jean-Louis' research with the dark blue and light blue, those are the graphs from eClimate Notebook. But another thing that I can tell you is when you're at risk for deterioration. So if it actually, the website itself like has algorithms that look at your data and say, you've had a sustained period of high temperatures. If you have organic materials, you're at risk for speeding up chemical deterioration, or you've had RH above 65% for X number of days, you're at risk for mold germination. And so that's when I say, like, you know, when the data tells us that we should or shouldn't have mold, we actually do have this tool that sort of helps take the mystery out of reading your data from your storage environment. Um, and so I just recommend looking at that website. It's got a lot of information on it too, a lot of educational material on it that talks about, you know, when you might end up with mold germination and why and how, as well as our sustainability book. And again, all of that is free. eClimate Notebook, um, as of now, we do have a free level, and then we also have a paid subscription, but it's not a whole lot. At least I don't think it. To me, it's not, for the value of the tool. It doesn't seem like a whole lot. So, but there's definitely free aspects to it and information. So to look at it, it has a lot of good info there. So hopefully that answers.
Oh, thank you. I believe this may be our last question. That has suddenly disappeared on me. There it is, from Gia Alexander, who asks, what about parchment or vellum with gold leafing?
Yeah, I would say anything other than printed ink on parchment or vellum. Yeah, gold leafing, paint, is susceptible to being friable, as in it'll sort of dissociate or just, you know, dislodge from the surface. Um, Vellum's a really interesting material, parchment slash vellum. You know, vellum comes from calves and parchment comes from all the other animals, goats and sheep and things. Um, but otherwise it's animal skin, right? It's treated, thinned animal skin. And its main sort of component is collagen. When collagen breaks down under high temperature and high relative humidity, you force water into it, it the structure of it loosens and it gelatinizes. It actually turns into gelatin. And so within parchment, especially historic parchment, you always have part of it that's still collagen and part of it that's gelatin. So the collagen itself expands and contracts and absorbs lots of moisture and releases lots of moisture, but the gelatin is extremely responsive. In fact, gelatin will absorb water, warm water especially, until it dissolves, right? I mean, that would be like if you soak it in water, right? The gelatin of it will dissolve, you know, and that's actually something we use in photography to our advantage. So when we have historic parchment and vellum, we don't know what portion of it is still collagen and what portion of it is gelatin. And so we don't know how much it's going to respond to relative humidity changes or temperature changes for that matter. And so I definitely think it needs more study for sure. And I definitely think studying different different configurations, different materials applied to the parchment is important, such as gold leaf and different paint, to kind of find out, like, at what point are you going to start having that material coming off the surface. So it definitely needs more study. I, at this point, would say be cautious. And again, you can implement sustainable environmental management. You can allow your RH to fluctuate. And if you have a couple of materials that you think are extra sensitive, you can create a microenvironment for them, you know, using silica gel and other materials that has a more constant or steady relative humidity. And that way you're saving a lot of money, but you're still taking care of those very special collection items. If you have a collection that's full of that stuff, then by all means, keep a constant relative humidity. No one will fault you for that. Yeah, it's just, you know, as I said, it's just expensive. So, you know, it's all about, you know, these ideas of dynamic environmental management. The first thing is knowing your collection, okay? It's all about knowing your collection and knowing the materials in your collection, as well as knowing your storage facility, you know, the building envelope. How will it perform? What are your collections of materials and what can they withstand? Yeah, and you know, there's different standards and things, you know, the American standards and there's British standards and there's, you know, international standards, and they all say something different, which is really confusing. I think for me, the most helpful are the British standards for storage environment for collections. Most people find them the least helpful because what it says is, it depends. Know your collection. What are your collection materials? So, yeah. I know people are just like, just tell me. But the answer is always, it depends. So now I'm rambling.
Well, it looks like we're out of time for our questions this evening, but on behalf of Rare Book School, I'd like to thank Al for a fascinating presentation and all of you for your participation. I'd also like to take this opportunity to mention that RBS's scholarships and fellowships are now open for our applications. If you're interested in learning more, be sure to visit our website, and we'll be posting the 2021 schedule there soon as well. So thanks again, everyone, and have a good night.